Okay, so here we are pretty well into chapter 19 now, our fourth lecture. We've talked about the amino acids at pretty decent length. We've started to talk about at least forming peptides or amide bonds there, and so we're building our way up to proteins. In this lecture, we're going to focus on really building those proteins, and we're going to look at the primary and secondary levels of protein structure, where we really start to combine enough amino acids that we're getting something interesting. And unfortunately, for those of you who aren't in love with proteins, something fairly complicated. So hopefully we can convert you if you've been put off by those complex proteins in the past, because now hopefully you're coming at them with a much better understanding than you have had in the past. Okay, so everything starts with the primary structure. So the primary structure of a protein is the particular sequence of amino acids. And this is what gives rise to that backbone of a peptide chain or a protein, depending on how many amino acids are involved. It's got to have quite a few to be a full-fledged protein, but obviously once we've got at least two combined, we've got a peptide chain forming. So there we have it. The particulars here that we've already covered in terms of naming, right? This one we have glutamic acid, histidine, and proline. So this would be glutamyl histyl proline. That sequence gives rise to a unique name, and that particular sequence, if we continue it for many more amino acids, we'll start to get protein, and based on the primary structure, we'll figure out at least the order of amino acids in the protein. And that's important information, although it's not that straight chain how the protein would occur in the body. It's just that straight chain is how we can figure out the sequence of amino acids. Okay, so let's talk about insulin. Insulin was the first protein to have its primary structure determined. And it actually has a primary structure of two polypeptide chains, which are linked by disulfide bonds. So you know we've got some cysteine residues there, right? And notice that those cysteine residues that link are not next to each other. They've got to be at least a few away from each other in order to get the right distance for bonding. So it's much more important to look at cysteine residues that can form disulfide bridges across or with a bend to the protein chain, because these straight chain things that we're talking about now for primary structure are all well and good for getting the order, but that they may not be anywhere near each other in the folded protein, aside from the ones who are bonded right next to each other. And those ones, if we have the two cysteine residues bonded right next to each other, notice they're not forming disulfide bridges with each other. They're forming with cysteine residues much later on or across another chain. I mentioned across the chains because in this case we have an A chain with 21 amino acids and then a B chain with 30 amino acids, and we have those linkages at those cysteine residues that form the disulfide bridges that are keeping these two chains together. And that's our primary structure. We'll also look at what happens when we get more complicated shortly. And here we are. It didn't take long to complicate things, right? The secondary structures. So one of the secondary structure features that we'll talk about is the alpha helix. So secondary structures describe the type of structure that forms when those amino acids form hydrogen bonds within a single polypeptide chain or between polypeptide chains. But again, this is not the disulfide bridges yet, although we've already seen that that happens in insulin. So an alpha helix, which we either can spell out or we can use the Greek symbol for lowercase alpha there, has a coiled shape held in place by hydrogen bonds between the amide groups and the carbonyl groups of the amino acids along the chain. So hydrogen bonds between the H of an amine group and the O an amide and the O of a carbonyl of the fourth amino acid down the chain. So this is where we're starting to talk about needing that three-dimensional space in order to get the right overlap. So we're not bonding necessarily, or hydrogen bonding in this case, with next door neighbors. We've got to go a few down in order to get that kink to the structure to form this secondary structure known as an alpha helix. And so here we see that particular helical structure forming from those connections from the carbonyl of one amino acid and then the amide NH of a 4 later residue, and that's what gives rise to these alpha helix patterns, and those are very common secondary structures in nature. And of course the story is that Linus Pauling figured this sort of thing out while he was sick in bed one day because he had all the bond angles memorized. Quite a brilliant individual who figured out essentially all of this protein structure stuff that we'll talk about here in chapter 19. And as wonderful and beautiful as the alpha helix is, it's not the only secondary structure out there. Beta-pleated sheets would form another type of secondary structure, and these happen when adjacent polypeptide chains or the same polypeptide chains with a rigid structure has the proline causing a bend in the polypeptide. So there's hydrogen bonds between the chains, there's R groups above and below the sheet, and this is typical of our fibrous proteins such as silk. So silk obviously prized for its softness and feel, and its key feature would be these beta-pleated sheets that as we said, form between adjacent chains or within the same chain when you have proline residues. And so here we can see why it's known as a beta-pleated sheet. So the pleated sheet, if you have ever seen things like pleated blinds or pleated pants or any of that stuff, the pleats are just the different folds, the back and forth in and out of the plane of the paper sort of thing. So there we have it, and we get those hydrogen bonds either between adjacent chains or within the same one if we happen to have a proline that will cause that kink itself because of the way proline, which was one I should have probably pointed out when we were talking about the single amino acids, proline has that sort of chain structure to it. The last secondary structure we'll talk about in this lecture, the triple helix, consists of 3 alpha helix chains woven together. Obviously we need large amounts of glycine, proline, hydroxyproline, and hydroxylysine in order for all those OH groups we need for the hydrogen bonding to get that tight a helix. This is found in collagen, connective tissue, skin, tendons, cartilage. That's where you're likely to find this very tight-knit triple helix secondary structure. And if you look at hydroxyproline, proline itself just is lacking that OH group. It's hydrogen in typical proline, but there you can see why proline gives a bend, because its amino group is not really free. It's part of that 5-membered ring, and that's why the proline, as we talked about for the beta-pleated sheet, is important for being able to impart a kink within a chain. It's also why hydroxyproline and proline are important for the triple helix structure we're talking about here. Okay, so before we leave our discussion of primary and secondary levels of protein structure, let's end with a learning check, as we often do. This learning check asks you to indicate the type of protein structure as either primary, alpha helix, beta-pleated sheet, or triple helix. So then we have the 4 different descriptions. So if you can match those up with those descriptions, then we'll see how you're doing. So stop the video here if you need another moment, and then start us back up when you're ready to check your work. Good luck. Okay, and so there we have it. So the primary protein structure is the sequence of amino acids in a polypeptide chain. It was B there down below. The alpha helix was C, the corkscrew shape with hydrogen bonds between amino acids. And our beta-pleated sheet was the polypeptide chains held side by hydrogen bonds, and then they come in and out of the plane as we saw that beta-pleated sheet picture. And then finally, the triple helix is 3 peptide chains woven together like a rope. Okay, so hopefully the triple and the 3 gave you a pretty good indication of which one that described. So if you did have trouble with this, if it's not making sense, please do reach out for some help, but hopefully things are coming together, and we're looking forward to the next lecture in chapter 19.